Before we leave our discussion on enthalpy and calculating enthalpies for reaction, there's one more topic to touch, and that's something known as bond enthalpies. These are also referred to as bond dissociation energies, although your textbook probably will not call them that. They are most commonly referred to as bond dissociation energies, or BDEs. And we can actually use those to help us figure out the overall enthalpy for a reaction. And I'll go through that with you. So bond enthalpy is the change in enthalpy for breaking a particular bond in 1 mole of a gaseous substance. So bond enthalpy, also known as bond dissociation energy, because we are breaking a bond, if you remember back to the beginning of this chapter, breaking a bond means that the change in energy has to be positive, and here in terms of enthalpy it is also positive, always positive number. So bond enthalpy, or BDEs, are always positive numbers. Let's just take, for example, Cl2 being that bond between the 2 chlorines being broken to give you just 2 chlorine atoms. That has a bond enthalpy of positive 242 kilojoules per mole. And just to show you more graphically represented, that's just looks more like this case here. We have a bond, and then we're breaking the 2 atoms apart. And just like heats of formation, bond dissociation energies, or bond enthalpies, are tabulated heavily. So there are many tables that have bond dissociation energies for single, double, even triple bonds between many different types of elements. So then, just like the question with heats of formation or enthalpies of formation, how are BDEs useful to us? How are bond enthalpies used in calculating the enthalpy for a reaction? Well, the enthalpy of reaction is written as the sum of the bond enthalpies of the bonds that are broken minus the bond enthalpies of the bonds that are formed. So this is always sum of BDEs of bonds broken minus BDEs of bonds formed. This is the one case where we have reactants minus products, because the bonds are broken in the reactants and they are formed in the products. So what does this look like here? Well, let's do a reaction between methane, which is CH4, and chlorine to generate methyl chloride, CH3Cl, and HCl. And we don't know the enthalpy of reaction for this equation. Well, we have this table here where we have this picture here where we can sort of describe what's going on in terms of just talking about bond enthalpies. So first off, if we talk about just breaking the bonds in the reactants, what we're doing is we are breaking a hydrogen off of CH4, because that's no longer there in the product. So we must be breaking a carbon-hydrogen bond. And we don't have a chlorine-chlorine bond in the products either, so we must be breaking the chlorine-chlorine bond. So we can think about just breaking those 2 bonds, and that would give us kind of this pictorial diagram here. And you can see that it's higher in enthalpy, or higher in energy, because it requires energy. The enthalpy is positive for doing that. However, then when we go to make bonds, making bonds is now downhill energy, is now negative, and that's going to be forming the carbon-chlorine bond and forming the hydrogen-chlorine bond. So if I look in the table, I can see that for a CH bond, the BDE is 413 kilojoules per mole. And for the Cl-Cl bond, that's 242 kilojoules per mole. And I have just 1 mole from the coefficients of the balanced chemical equation. I just have 1 mole of each reactant, and I'm only breaking 1 bond from each one. So I'm just breaking 1 mole of bonds. And you can see the bonds formed. We have the BDEs of those as well. The CCl bond is 328 kilojoules per mole. The HCl bond is 431 kilojoules per mole. So we simply plug that into the equation. Bonds broken, 413 plus 242, minus bonds formed, 328 plus 431. And we come out with an enthalpy of reaction of negative 104 kilojoules per mole. Now, if we did this just as where we just have 1 mole of CH4 and 1 mole of chlorine, then that would just end up being negative 104 kilojoules. If we had a different mass or starting mass of those, we could then figure out the number of moles of that and then use that to figure out the total amount in kilojoules using this amount in kilojoules per mole. So let's do one more example of this then. So we've got carbon with 3 bromines and a hydrogen reacting with ClCl. And we end up forming a new carbon-chlorine bond and again a chlorine-hydrogen bond. So if I look at this, what I can see is that the bonds that I have broken is the CH bond. That's no longer there. You just look for whatever's no longer present to see what's broken. So the CH bond is no longer there. The ClCl bond is no longer there. So those are my bonds broken. So if I want my delta H for reaction, that's going to be bonds broken minus bonds formed. So it's going to be CH, ClCl, and then on the other side, the bonds that are formed, I'm making a CCl bond, and I'm making an HCl bond. And so I substitute those numbers in, 413 for CH, ClCl, that one we had here as being 242, 242, CCl, down here at 328, and then HCl, frequently the H is listed first, 431. And if I go through all of this, what it'll come out with is actually the same answer as I had on the previous page, because we're making the same bonds, a carbon chlorine and a hydrogen chlorine, and we're breaking the same bonds, a carbon hydrogen and a chlorine chlorine bond. So the net enthalpy of reaction here is going to be the same as the previous example. And I will come out with that here, 431, negative 104 kilojoules here. Now you may wonder, we have different reactants. We've got bromines present instead of hydrogen, so why is the enthalpy the same? Well, notice here that these are average bond enthalpies. The very, very specific CH bond dissociation energy for this particular CH bond isn't going to be exactly 413 kilojoules per mole, but it would be close to that. And the CCl bond here will not be exactly 328 kilojoules per mole, but it will be close to that. And so this allows us at least a close approximation of what the overall reaction enthalpy would be, just using tabulated values for average bond enthalpy.